dy dx equals cosine x, which is in parentheses, and then e to the power of y plus sine x. And then y equals 0 and x equals 0.
Y equals 0, x equals 0. Okay. All right, so clearly this is a separable differential equation because it's got x's and y's with our dy dx. So the first thing we'll want to do is rewrite e to the y plus sine x as e to the y times e to the sine x. That's just exponent rules, right? E to the a, e to the b multiplied together is e to the a plus b. And so then we can bring this e to the y to the other side. So that will give us dy over e to the y equals cosine x e to the sine x dx. Everybody good with that so far? All right. On the left-hand side, we're going to have to rewrite this because dy over e to the y is not something we can just simply integrate. So we could rewrite that as e to the negative y dy. And then on this side, we can't just integrate that without doing a u sub. So we'll let u equal sine x. And du will be cosine x dx. So this side will become e to the u du. And then this side we'll have to do a u substitution with it also, because we're going to want to integrate both of these. This one, I'm going to have to let, well, since I had to use du, let's let v equal negative y, and dv will be negative dy. So I got to put in a negative and a negative. So we'll end up with negative integral e to the v dv equals integral e to the u du. Everybody good with that that one so far?
Yep.
All right. So over here, this just becomes what? Negative e to the v, or negative e to the negative y. And this becomes e to the u, or e to the sine x, plus our constant. And when x is 0, sine of 0 is 0, e to the 0 is 1. And over here, when y is 0, e to the 0 is 1, with a negative in front would be negative 1. So our constant should be negative 2. And so we've now got negative e to the negative y equals e to the sine x minus 2. We will divide everything by a negative. So that makes it 2 minus e to the sine x. Take the natural log of both sides. And then divide by a negative. And that's our final answer. And in terms of interval of validity, we can only take the natural log of things that are positive. And e to the sine x, well, we know that sine x is always going to be between negative 1 and 1. So the smallest value that sine x will be negative 1, which will make this 2 minus e to the negative 1, or 2 minus 1 over e, which is always positive. And then the largest value that sine x will be, it would be 1. So that would be 2 minus 2 minus e there. And so that one ends up giving us a negative right there. And so we'll have to find a place. I might have put negative infinity to infinity on the interval for that one, did I?
Yes.
I did. That could be a problem. That's a bummer. All right, let me think about that then for a second. All right. So we'd have to see when that thing is greater than 0. So 2. Let's get a new page for that. That was the function I had, right? 2 minus e to the sine x natural log of that with the negative out in front. So this gives us that e to the sine x is less than 2, or sine x is less than the natural log of 2. Or what can we do with that? Take the inverse sign. So x is less than the inverse sine of the natural log of 2. And let's see. Think about that. There should be another discontinuity on that. No, I think that's it. X just has to be less than the inverse sine of natural log of 2. And greater than, what does that need to be greater than? I think it's going to be negative 3 pi over 2 plus that. Yeah, negative 3 pi over 2 plus the inverse sine of the natural log of 2, which is just the value that you end up getting if you go 3/4 of the way around. Oh man, what a mess of a problem. That you end up getting if you go 3/4 of the way around, which would be the same reference angle as inverse sine of natural log of 2, but giving you a negative value there. So that should be your interval. If that interval didn't make sense to you, don't worry about it. That should be the interval, and I will not give you one with any sort of interval that difficult tomorrow. Man, that was a bad mistake I made there, putting negative infinity to infinity there. Any other questions on that one? Mostly with getting this, because that's how you get the solution. But
I have like a general question.
okay.
When you're solving for these, is it typically easier to solve for C before you solve the whole equation for Y?
Yes, I would normally do that.
Okay, thanks.
I feel like that's how we've done most of them, is find C and then solve for Y. So, yeah, that's definitely what I would do. Any other questions? Nothing else for the quiz, nothing else from the ones that we did that I posted yesterday. All right, number 4. What was number 4?
It was dy dx equals 4xy squared. And then,
Sorry, right?
and then y of 0 equals 1.
Okay. So again, separate the variables. So dy over y squared equals 4x dx. And then dy over y squared, that's like y to the -2 dy. And this side will become 2x squared plus a constant when you integrate it. And then now we need to integrate y to the -2. So what do we get if we integrate y to the -2? We should get -1 over y. And we'll plug in 0 for x to get constant equals, and then plug in 1 for y to get -1. So -1 over y equals 2x squared minus 1. And you can take the reciprocal of this to just get -y equals 1 over 2x squared minus 1. Or y equals 1 over 1 minus 2x squared. Or you could just put a -1 in front of it also, it'd be fine. And then for the interval of validity for that one, the denominator can't be 0. So that tells us that x squared can't be 1/2, or x can't be positive or negative square root of 1/2, which would be 1 over root 2. And since x equals 0 falls between positive and negative 1 over root 2, we'd say -1 over root 2 to 1 over root 2. Does that make sense or no? Other questions? All right, any questions on the limits questions that we had from the multiple choice? Anybody? Questions from the limits multiple choice?
I have a question about like a symbol. So I think 20 and 29 deal with like limits of x in like little brackets. I don't really know what that means.
Ah, okay. Yeah. So probably like this, or is it like this with 2 brackets or with 1 bracket? So
One bracket.
1. Okay, yeah. Did they call it the greatest integer function?
Yeah.
Okay, yeah, that's sometimes it's denoted with double brackets, but that's fine. The greatest integer function is this one. You You've seen it before, probably. It's a
Oh
step
yeah,
function.
yeah,
So,
oh yeah.
so it says y is the greatest integer less than or equal to x. So if x is 1, the greatest integer if x is 0, the greatest integer less than or equal to 0 is 0, because 0 is equal to 0. But if x is a half, then the greatest integer that is less than or equal to 0, less than or equal to half is still 0. So y is still 0. All the way up until you hit 1, right? At 0.99999, the greatest integer that is less than or equal to 0.99999 is still 0, so it's just this flat line. But at 1, it jumps up to 1. And it does the same from 1 to 1.99999, and it jumps up to 2, and so on. So from the left-hand side, all these limits equal the lower value. From the right-hand side, they equal the upper value, but the two-sided limits at these integer values don't exist. But the limits at like the interior piece of that, so if I said the limit as x approaches a half, it'd be 0, because from both the left and the right, it's 0. Does that make sense?
Okay, yeah, thank you.
Any other questions from the limits multiple choice? Okay, 37. Let's see, let me pull out the book. What I got those from 37. Give me 1 second here. So what is 37? It's the limit as x approaches 0. This is one of the challenge ones. This one's intended to be difficult. 3 plus inverse tangent of 1 over x, right? And we got a bunch of options, negative infinity, and then root 3 minus pi over 2, root 3 plus pi over 2, infinity, or it doesn't exist. So as x approaches 0, we're looking at the 1 over 0, which is like this going towards infinity, right? So we're really looking at what is the inverse, this is inverse tangent, right? What is the inverse tangent of infinity? Well, the inverse tangent of infinity is pi over 2, but only from one side. So we kind of got to think about what's happening to this thing from both sides. So as x approaches 0 from the right, what does inverse? Well, as x approaches 0 from the right, the inverse tangent, we end up with the inverse tangent of infinity, right? Within here, which equals pi over 2. But as x approaches 0 from the left, we end up with the inverse tangent of negative infinity, which is negative pi over 2. And so if we look at this as two different sides of it, from the right, it should be approaching root 3 plus pi over 2. And as we approach from the left, it should be approaching root 3 minus pi over 2. And so since from the right and the left-hand sides, it's approaching different values, we would know that this limit doesn't exist at all. Does that make sense? And we could, let's see here. What was the function again? I just went away on mine to Desmos. What was it? It was square root of 3 plus the inverse tangent of 1 over x, right? And you can see that's exactly what we got going on here is we've got a jump discontinuity here at 0. So from the right-hand side and from the left-hand side, we get different values. That's a tough one.
Can you do number 39? It's similar. It's the limit as x approaches 0 of 1 over 2 plus 10 to the 1 over x.
Saying the limit is x approaches 0 of what? 1.
Divided by 2 plus 10 to the 1 over x.
Okay.
Yeah.
And let's see, 39, right? Okay, so it's got 0, a 12th, a half, a third, and doesn't exist. There's our options for that one. So yeah, we're gonna sort of take a look at the same thing. This 1 over 0 thing can either be positive or negative infinity, depending on which side we're approaching from. So we really want to take that into account here. So as x goes towards 0 from the right, then y is going towards 1 over 2 plus 10 to the, if x is going to 0 from the right, that's 1 over, and 1 over a very small number, that's positive infinity, right? And so this ends up being 0 because we've got 1 over 2 plus a very large number. But as we approach 0 from the left, y approaches 1 over 2 plus 10 to the negative infinity. And then that negative infinity dominates this 2. So the 2 becomes insignificant. The 10 to the negative infinity flips up to the top and becomes infinite.
So again, non-existent.
Again, yeah, non-existent for that one. So, and if we wanted to look at it, what was the function again? It was 1 over 2 plus 10 to the 1 over x, right?
Yeah.
You can see again that there's a jump discontinuity there. So from the left and from the right, you get different values. Good?
Yeah, good there.
Okay. Other questions? I shouldn't have said infinity there though. That's not true. That doesn't, just because this is not multiplied by this. So this is not, these are not combined together. This becomes 1 over 2 plus 0. 10 to the negative infinity is just 1 over 10 to the infinity, which is 1 over 2 plus 0. So that goes towards a half, not towards infinity. But still
Okay.
not the same. So doesn't exist. Other questions from the multiple choice there? All right. There's no more. Then we will move on to this problem right here. This looks like a good one for us to do, right? We want to find the area of the region in the first quadrant that's bounded above by y equals square root x and below by the x-axis, and the line y equals x minus 2. Let's see. Square root x, x minus 2, the region in the first quadrant. That's this region, right? True?
I think we did this one like 4 times yesterday.
No, that's the problem. We only did this one 3 times yesterday, right?
Oh, right. Okay.
We only did it 3 times, so now we've got to do it a 4th time because we only did it 3 times. But yes, we did. We did do this one 3 times. All right. So yesterday we did this one by splitting it up into 0 to 2 and 2 to 4, right?
Yeah.
And we also did it by going 0 to 4 of the upper function minus the x minus 2 and then knocking off this triangle. We also did it by doing root x from 0 to 4 and knocking off this triangle. And there's actually another way that we could do this. And we have to look at it a little bit differently. So what we want to do is try to integrate this in terms of y. So we are going to see if one function is always to the right of another function for all y values in the region. So the y values in my region go from 0 to 2, right? We found that point yesterday to be 4, 2. So for every y value that you choose, suppose this y value, which function is to the right of the other one?
X minus 2.
X minus 2, right? What about this y value?
Same.
Same thing. What about this x or this y value?
Still x minus 2.
Yeah, no matter what y value I choose, right? I choose any of those y values I want. The same function, x minus 2, is always to the right of the square root x function. So if we want to, and sometimes we will need to do this, we can integrate in terms of y, going from the lowest y value to the highest y value. And then we will do the rightmost function minus the leftmost function. But they have to be in terms of y. So y equals x minus 2 was our rightmost function. And y equals root x was our leftmost function. What is y equals x minus 2 in terms of y? X would be y plus 2. Right? And what about this one? This would be x is equal to y squared. Agreed?
Yeah.
So we could do this as the integral from 0 to 2 of y plus 2 minus y squared dy. Any questions on that setup there?
So the whole thing about like one has to be to the right of another,
Mhm.
is there like some reason for that, or is it?
Well, just like when we did in terms of x, we did the upper function minus the lower function, right? The one with the larger y values minus the one with smaller y values. Well, now we're doing the ones with larger x values minus smaller x values.
Okay.
Yeah, so effectively, we're finding the area between the line and the y-axis, and then subtracting the area between this curve and the y-axis. Does that make sense?
Yeah.
Okay. So we end up with y squared over 2 plus 2y minus y cubed over 3 from 0 to 2. And 2 squared over 2 is 2, right? Plus 2 times 2 is 4, minus 2 cubed is 8 over 3, minus 0 plus 0 minus 0. And we got 6 minus 8 thirds. 6 is 18 thirds minus 8 thirds is, once more, just like yesterday, 10 thirds units squared. And now I promise we are finished with that problem. We will not do that problem anymore. Good?
Yeah.
Yep.
Any questions on how to integrate this thing in terms of y?
Why did you only go from 2 to 0?
Well, I went from 0 to 2, not from 2 to 0. But I went from 0 to 2 because we went from the lowest y value to the highest y value. When we do it in terms of y, we have to use y values instead of x values.
All right.
And we determined yesterday, we determined the coordinates of that point were 4, 2. So does that make sense?
Yeah.
Perfect. All right. Let's do another one. See if we can find the area of the region enclosed by y equals x cubed and x equals y squared minus 2. So first off, what does y equals x cubed look like? We should know what that one looks like, right?
Yeah.
It's a cubic, right? Something like that. And what does x equals y squared minus 2 look like?
Like a square root function. So if you solve for y, you get like y equals x plus, or y equals the square root of x plus 2.
Okay, well, technically you get plus or minus that, right?
Okay.
So it should look something like a parabola laying on its side. All right, so this is the square root x plus 2. This is the negative square root x plus 2.
But isn't that like not a function? So you like have to omit one of the,
No,
no? Okay.
this is the equation that was given to us. Nothing in here says that this was a function, that it has to be represented as a function. It is a function in terms of y, right? So it would, if we were to say this is x of, or if we called it, f of y, that's what this is. This is x equals f of y. It's a function in terms of y. It passes the horizontal line test rather than the vertical line test. But that's sort of beside the point. It doesn't matter what this equation looks like. It doesn't have to be a function. We still have to draw every solution to this equation, because the graph of x equals y squared minus 2 is the set of all points that solve that equation. So as we look at this region, right, if we look at this region, is one function always above the other function?
Yes.
What about right here? Oh, that's not very
Oh, wait, no.
pretty close to that over there. And in fact, my sketch isn't great. Maybe we should do this on Desmos just to get a better sketch. I had what, x cubed, right? And x equals y squared minus 2. I think if you look on Desmos, you can pretty clearly see that there are some x values where x equals y squared minus 2 is both the upper and the lower function. True? Like at negative 1.5, for example. Agreed? You all see that the x equals y squared minus 2 represents and the bottom of that region. All right, that's a problem. Now, it's a problem that you can get around sometimes, but not always. In this case, we could, if we wanted to, get around that problem because we know this function is symmetric across the x-axis and we can deal with it, but we're not going to. We're going to say, is for every y value of this region, one function always to the right of the other equation?
Yeah.
Yeah, the cubic, for every y value, starting at the bottom of the region up to the top of the region, the cubic is always to the right of this parabolic function. So we should be able to do the right equation minus the left equation. And so we'll have to turn the one that's y equals x cubed into x equals the cube root of y, or y to the 1/3. And we should be able to integrate the right one. And which one is the right one? It's the y to the 1/3, right? Minus the y squared minus 2 equation. And we'll need to do something here to figure out where these intersect. So we'll set them, well, we can't exactly set them equal to each other, but we could could go in here and say, well, we know that if y equals x cubed, if x equals x to the 6th minus 2, and we could solve that for whatever x values and then plug them in to find y values. Or better yet, we could say, since we know that x equals y squared minus 2, we could say y equals y squared minus 2 cubed, and that would tell us the y values at which they intersect. And so if we were to use our graphing calculator, we could figure out where these intersect. But since we happen to have it in Desmos already, the y values are -1 and 1.793. Right, -1 and 1.793. I'm going to go to Desmos to show you that. -1 and 1.793. So we'll integrate from -1 to 1.793. Obviously, this is an annoying value to evaluate in this. So we'll just let our graphing calculator approximate that integral for us. And what do we get? Anybody? What'd you get?
At 4.215.
Anybody else agree with that?
Yeah, I got that as well.
All right, cool. Easy enough. Any questions there? That's the idea of integrating in terms of y, and that should allow you to finish up the rest of what's on your homework assignment, because there might be a couple in there that need to be done with in terms of y. So now we're just going to do a couple more quick little easy area problems just to set up and make sure we understand conceptually what we're doing. We're not necessarily going to evaluate this one. Just want to make sure we know what we're trying to do for each of these. So if I wanted to find the area of the region or regions bounded by this parabola, this line, and these two vertical lines, the first thing we'd want to do would be to graph them, right? And we'd see that looks something like that. And when I put in x equals -2 and x equals 5, we'd see that there are 3 different regions here. This one with the green, blue, and red right here, one with just the red and the blue, and then another with the red and the blue and the purple lines. Everybody agree that there's 3 different regions there?
Yeah.
And so how would we set this up?
3 different integrals.
3 different integrals, right? And we'll note the intersection point here is -1 and the intersection point here is 3. And that from -2 to -1, the parabola is above the line. And then between -1 and 3, the line is above the parabola. And from 3 to 5, the parabola is back above the line. So what would our integral look like? It would be the integral from -2 to -1. And which one did we say was above for that? The parabola, right? We add to that -1 to 3 of the line minus the parabola. And we'd add to that 3 to 5, once again, of the parabola. Minus the line. Conceptually good?
Can you repeat what, like, explain why you just did that again?
Why what?
Like, can you explain where you got the integrals from?
Yeah, so it's always the upper function minus the lower function to find the area of the regions between them. So from -2 to -1, the parabola is above the line, so it's got to be parabola equation minus linear equation. Then from -1 to 3, the line is above the parabola, so it's got to be the line minus the parabola. And then from 3 to 5, the parabola is back above the line, so it's got to be the parabola minus the line. So we got parabola minus line, line minus parabola, parabola minus line, and then each of the different intervals on which that was true.
Okay, got it. Thank you.
Mm-hmm. All right, and let's do one last one. In fact, why don't you guys do this one on your own? I'll give you 2 or 3 minutes, and then we will work through it together to make sure you got it. Ready, go. All right, this one we should have been able to graph and see pretty clearly. Sine x and cosine x. And we're going from 0 to pi over 2. Pi over 2 is where cosine crosses the x-axis and where sine hits its max. Right, so this is our sine x, and this is our cosine x. Where do they intersect? Where does sine x equal cosine x?
Pi over 4.
Pi over 4. A lot of other places too, but pi over 4 is the one we care about, right? Because we're enclosed by pi over 2 and x equals 0 also. So we're talking about these 2 regions here. So the first one can be found by the integral from 0 to pi over 4 of cosine x minus sine x dx, since that's upper minus lower. And the second one can be found by doing pi over 4 to pi over 2 of now sine x minus cosine x. Is that what you all did to set it up?
Yeah, I have a quick question. Do you think this would be a calculator problem or a non-calculator problem on the AP test?
Definitely non-calculator.
Okay.
Integral of cosine would be sine x, and then integral of negative sine would be plus cosine from 0 to pi over 4. And then we will add to that, integral of sine is negative cosine, and integral of negative cosine is negative sine from pi over 4 to pi over 2. And the sine of pi over 4 is root 2 over 2, and the cosine of pi over 4 is root 2 over 2, and then 0 and 1 for sine and cosine of 0. So far, good?
Yep.
All right, cosine of pi over 2 is 0, so that's 0. Minus the sine of pi over 2, which is 1. And then minus negative cosine of pi over 4 is negative root 2 over 2. And minus another root 2 over 2. So if we combine all of this together, looks like we've got a root 2 over 2 and a root 2 over 2, which is just root 2. And we've got another positive root 2 over 2 and another positive root 2 over 2, which is another root 2. So we got root 2 plus root 2, which would be 2 root 2. And then we got a negative 1 and another negative 1. So 2 root 2 minus 2 units squared. Good or no?
Good.
All right. That's it for today and for area in general.